fire safety deserves top priority. Every day, dozens of fires rage in the Benelux, causing the death of dozens of people and injuring thousands. Burns are some of the most serious injuries a person can suffer. The damage from the fires costs hundreds of millions of euros every year. More than half the companies who've had a big fire go bankrupt within 3 years. Moreover, every fire generates harmful consequences to the environment. The images in this film show the possible effects if the fire safety of the insulating materials used are not taken into sufficient consideration. These materials can contribute significantly to fire propagation due to the release of combustible gases, smoke development, and falling burning droplets. In this film, we'll show you the differences in fire reaction and fire behavior on the basis of objective scientific tests. As you'll see, the right selection of such insulation material can literally be of vital importance. Since the introduction of the new Euro fire classes on the 1st of February 2002, a clear classification system has been developed for building products for the entire European Union. The new method can be used to test all products for their fire behavior in the same way. 4 small-scale fire tests have been designated in order to arrive at the Euroclass classification. The SBI or Single Burning Item Test, the Bomb Calorimeter, the Small Flame Test, and the Non-Combustible Test or ISO Furnace Test. The small-scale SBI test is derived from a much larger fire test, the realistically dimensioned room corner test. In this test, a room is covered with the products to be tested. It examines when flashover takes place. Flashover is a very high-temperature fireball particularly feared by firefighters. The European classification fire tests are carried out, among others, by the Warrington Fire Ghent Test Laboratory. This test laboratory is a spin-off of the University of Ghent in Belgium. The laboratory has an established reputation and is an authority in the field of fire safety in Europe. For this study, Rockwool tested basic insulation material, Rockwool, EPS and PIR alu, as well as sandwich panels. Before the fire test took place, various zero measurements were taken without test sample. Let's take a look at the test sample fire measurements. In the room corner test, about 30 square meters of insulation material is affixed in a room. The sandwich panels, or the insulation material, are exposed to a 100 kilowatt flame in a corner of the test room for 10 minutes, followed by exposure to a 300 kilowatt flame for 10 minutes. The capacity released, the smoke production and the temperature are measured over time just above the burner at 7 different locations on the ceiling, as well as at various heights in front of the doorway. In addition, pressure and radiation are measured at the floor level, and radiation is measured at a distance of 1 meter in front of the doorway. Any products that do not result in flashover during a 20-minute period in the room corner, the reference test, are products that do not or that barely contribute to fire propagation. Products in fire classifications A1 or A2 always comply with this. If flashover does occur, the phase in which this happens is checked. Next, the small-scale fire tests used to establish the Euroclass. The SBI is designed to determine classification A2, B, C and D that simulate a starting fire, for example, in a burning waste bin. The surface of the material to be tested is exposed to a 30 kilowatt flame for 20 minutes. The effect of the combustible flue gases on fire propagation and flashover is not taken into consideration in the SBI test. The oxygen consumption and the smoke and CO2 production are checked. Oxygen consumption is measured because it's proportional to the capacity released in a fire. For the so-called zero measurement, the temperature is measured at 3 different points near the corner at 1.5 meters above the burner, in the corner, and on both sides 20 centimeters from the corner. The radiation is also measured at a 45-degree angle at a height of 1.6 meters. This small flame test is used for product classifications B, C, D and E. It's used to test the combustibility of a material by means of a candle flame. It's determined whether a product ignites easily and quickly and whether the fire then spreads quickly. The zero measurement takes place by measuring the temperature change at the surface of a non-combustible base. The flame is directed to the bottom at the cutting edge. Measurements are taken at 2 centimeter intervals up to a height of 15 centimeters. During the test involving the test sample, the flames may not spread further vertically than up to the mark at a distance of 15 centimeters from the point where the test flame is applied. The bomb calorimeter is used to measure the energy content of products. An accurately measured amount of product is ignited in a hermetically closed small cylinder or bomb at a pressure of 30 bar using pure oxygen. The combustion value or energy content of the product is measured by registering the temperature increase of the surrounding water jacket. This combustion value is expressed in megajoules per kilogram and must remain below a certain value to comply with class A1 or A2. The zero measurement does not take place in this test, since doing so would require test material. In order to measure the incombustibility of a material, the so-called ISO furnace test is used. This test simulates a completely developed fire at the moment of flashover. In this test, a small sample of a material is exposed to a temperature of 750 degrees Celsius in a furnace for 60 minutes maximum. The extent of temperature increase, weight loss and ignition time at this temperature determine the incombustibility of the material. The zero measurement here takes place by measurements at 3 places in the furnace without a test piece for a 1-hour period. Temperatures are measured at 1 centimeter from the wall, in the middle of the furnace at half the total height, and on the surface of the test sample. What's striking in this test is the increase in temperature in the test furnace. For rock wool, the temperature in the furnace increases by 18.08 degrees Celsius. For PIR, this increases 154 degrees Celsius. The reason for this is that this plastic burns as a result of the sudden release of flue gases that cause ignition. EPS shrinks when it burns. The temperature increases only slightly due to the chimney effect that occurs in the process. Furthermore, the test results show that plastic insulation materials lose 100% of their weight and burn up entirely. Thus, PIR and EPS burn up completely at 750 degrees Celsius and are therefore combustible. Rock wool has an ignition time of 0 seconds. This means that no flames are visible at 750 degrees Celsius. Moreover, the weight loss of rock wool is very limited in the ISO furnace test. 3.53%, which is due to the binding agent in the rock wool. The insulation material hereby amply complies with the criterion for classification as a non-combustible material. This small flame test shows that rock wool does not ignite at this low temperature load of a maximum of 180 degrees Celsius in the zero measurement, identical to a candle flame. PIR carbonizes when exposed to this low temperature, and EPS shrinks away from the fire. On the basis of the small flame test, we can conclude that PIR and EPS are not easily combustible at this relatively low temperature due to the use of fire or flame retardants. However, these fire retardants do generate unpredictable reactions to fire that's progressed further with a higher temperature load, such as in the room corner. Since the energy content of rock wool is less than 2 megajoules per kilogram of product, rock wool is non-combustible. So this insulation material no longer has to be incorporated in the fire load calculation. The measured energy content of PIR is about 30 megajoules per kilogram, and that of EPS more than 40 megajoules per kilogram. PIR and EPS are thus combustible and contribute to the total fire load.